Go for it, Andy.
Okay, right. Well, welcome to those attending tonight. I think this is the first online Teams presentation that the Reading Area Committee of the IMechE has put on. I know we're edging towards physical events again once we're allowed to, but at the moment I think this is the first one. So there's a bit of trial and error with this tonight, with the Teams presentation. However, that doesn't detract from the importance of the subject or the people that we've got joining us tonight. So welcome to tonight's presentation. It's Emergency Planetary Cooling, the Need and the Tools. The presentation is being recorded first and foremost, so for all those who registered for tonight's event, and a lot of them I don't think have actually joined the meeting, we'll be sending this presentation, a link to it on YouTube, to the recording after the meeting, so it will be available, not in the live form, but on YouTube. Okay, so the event is presented by Clive Elsworth, who co-founded the Citizens Climate Lobby UK in 2014, and he is an independent engineer, scientist, working with Franz Oeste and other chemists to further develop and promote the Iron Salt Aerosol method for methane removal and CO2 drawdown from the atmosphere. He chairs a fortnightly Zoom meeting attended by dozens of senior scientists and nature-based oceanic and atmospheric cooling scientists, and looking at different methods of achieving that. We're delighted to have two very important guests joining us tonight in addition, who will be supporting Clive's presentation and available during the question and answer session at the end of the presentation. Stephen Salter, who is the Professor of Engineering Design at the University of Edinburgh. He has been championing marine cloud brightening for the last decade or so, and is leading efforts in that, in different proposals there and the ways forward. Franz Oeste from Germany, he is a retired chemical engineer and environmental chemist. And he has been pioneering the Iron Salt Aerosol method for the last 20 years and developing methods and proposals on how that can be deployed. And that's all going to be discussed tonight during the presentation by Clive. Can I ask the attendees to please use the chat function on Teams, to ask any questions, or to wait until the end of the presentation when there'll be an opportunity to, unmute yourselves and ask questions. Please, everybody attending, mute your microphones on Teams and keep your outgoing video functions in the off position with the strike through on the camera, please, just to enable Clive to give his presentation and get through it on time. Okay, so enough from me. Over to you, Clive. I'll introduce Clive Elsworth.
Thank you very much. Thank you very much, Andy. How's that? Can you see that okay? The start screen. Okay, well, thank you for having me at the IMechE for this presentation. So I'm going to try and get through these slides quickly so that we can have as much time for question and answers at the end. So okay, so here's the agenda. How and why is the Earth warming? Briefly, risks of continued warming, and then moving as quickly as possible to the immediate cooling options. And we favor nature-based options, and the two I'm going to talk most about are marine cloud brightening, as Andy has just said, and Iron Salt Aerosol. So why is the Earth warming? Well, there's an energy imbalance. There's more heat coming in than heat going out, and you can liken it to a kettle. You switch a kettle before it's switched on. There's no imbalance. As soon as you switch it on, it heats up. There's more heat coming in than going out. Once it's boiling, it's the same, so it's a zero again. And once you switch it off, the heat comes out very quickly, and there's not much heat going in. Kettles boil fast. The Earth is warming very slowly. Actually, the Earth has responded a little bit. It's heated up a little bit, so there's a little bit more energy coming out than used to. But it hasn't. It's not keeping up with what's called the radiative forcing. So, very briefly, here we are showing these are net forcings. It's the energy input is measured in watts per square meter. So there's now 3.2 extra watts per square meter coming in than used to before, pre-industrial, and it's responded by 2.3 watts extra heat coming out. So the difference you can see is 0.9. Now here's a plot showing how that's changed, and of course to say it's 0.9, well, whose measurement do you agree with or do you believe? There's lots of different measurements, so I've put this dashed line across here at 0.9 to show that it's kind of roughly about in the middle there. You see other people specifying 0.9, so that's that. These are interesting points here. There's a lot of cooling, three major cooling events here corresponding with major big volcanoes basically. It's a bit of a red herring because we don't really favor mimicking volcanoes. More on that in a moment. This slide is here to show, once again, the net absorbed. Actually, this slide's already out of date. It says 0.6 watts per square meter, and you've just seen me say it's 0.9. But the main point of this slide is to show a great deal of energy comes in from the sun and is immediately reflected out again. So you see 77 reflected watts per square meter reflected by clouds, and it's clouds that are really the subject of this presentation. Marine clouds, as these low-lying stratocumulus clouds, tend to provide a cooling effect, and it's these high clouds, cirrus clouds, that provide a net heat trapping effect. Okay, so but before we get to that, what's the current approach to solving climate change, if you call it that? Well, it's to, as we know, reduce our emissions. Now you can see good intentions aren't working. These are the COPs, Conference of the Party meetings. We've got Glasgow coming up very soon, but you can see the effect that they've had on CO2 concentration in the atmosphere. It's just been rising inexorably up. This is slightly interesting. The 1990s, there was a recession that seems to be related to economic activity more than anything else. Okay, so that's the strategy. Just try and reduce emissions, and it's not working. So, and what's going to happen, and what is already happening with this rising temperature? Well, today's warming, you can see, is inducing further emissions. The main greenhouse gases which are providing this radiative forcing are CO2 and methane, and this is just some of the components of the extra emissions that I put here. I've had to leave some off. There isn't space. So huge areas of permafrost in Siberia and Canada are melting, and then that biomass decays, gives off CO2. We all know about forest fires. When soils warm up, they give off CO2. Once again, it decays. There's a very large amount, 1,500 gigatons. That's a huge amount of carbon in soils. And Franz and I have done some very basic calculations and seen that it's rather consistent with actually Bill Gates's book recently, that sort of the order of about 50 gigatons of CO2. So 40 gigatons of human caused CO2, and then an extra 20% of that. So is an extra, but it's actually 9 gigatons. Okay, so scientists are calling this the compost bomb. Methane, once again, permafrost, wetlands. There's another risk here of some scientists are very worried about methane hydrates in shallow Arctic seas, which are literally bubbling up and coming out of the sea. This is a Russian scientist, Shakova, who says 50 gigatons could be released abruptly at any time. That would, according to Peter Wadham's, climate scientist, increase temperature by 1 degree centigrade. So pretty bad. What would be the effect of reducing emissions if we could do it? Eliminating all global emissions would, theoretically stabilize air and land temperatures, but they'd be much higher than now. Ocean warming would be decelerated, but it's still got a long way to catch up. That most of the energy is going to the oceans. That's what's providing the inertia that's preventing the Earth heating up much more quickly. So this would not be good. We'd still get catastrophic sea level rise. We'd lose huge amounts of infrastructure. Two ways to cool the Earth. This is very high altitude look. Return atmospheric. So this is CO2 equivalent, including the other greenhouse gases, back to basically pre-industrial 300 parts per million, which means removing 1 trillion tons, and then maintaining net zero emissions. So take decades at best. Forgive my flippancy here, pigs might fly. And immediate cooling by increasing the Earth's albedo. So reflectivity, as I was just mentioning, perhaps by increasing clouds. I'm not going to talk really about heat transport mechanisms, but really both 1 and 2 are needed. So this does need to be done as well, because otherwise, it's going to be impossible to keep the planet cool if greenhouse gases just keep going up and up and up. But these cooling interventions are considered geoengineering. We prefer the term climate repair, or people trying to think of nicer words, but it doesn't hide the fact that unintended consequences, what could happen that we haven't thought of, and how do you govern such a thing that's going to affect the whole planet? And then, so really just flagging these 2 problems: the moral hazard argument. What about these sort of evil fossil fuel companies that want to keep emitting CO2? That gives them, a get out of jail free card to just keep emitting CO2. But it's interesting to see where are the extra emissions coming from. So this is a serious. I'm frankly quite worried about this as well. It's not that the fossil companies are evil, but just that once you have some solutions, it just becomes very difficult to focus people's minds on reducing emissions. So, but where is this emissions growth happening? It's mostly in the developing world. So Britain is being reasonably successful at reducing emissions. I mean, you could argue we've exported most of our emissions to China. So I'm not going to get into all that. But basically, you can see that the developing world, people have the audacity to want to drive to work every day and have schools and health services and things that we take for granted. And it's the same unsustainable system that still hasn't been really transformed. You could argue, okay, but renewables are cheaper. But so how come that 600 coal-fired power stations were planned in only 5 Asian countries, including Japan, which I was a bit surprised about. So you might say, oh, that's changed. This is old news. Well, June 2021, not so long ago. I don't think it's changed very much since then. So on to our proposals, our solutions for cooling, albedo modification options. So here's mimicking volcanoes. It's called stratospheric aerosol injection. So putting an aerosol right up in the stratosphere. I put a big red cross against it. The main reason is there are proponents of this. Franz and I in particular, especially Franz, is worried about the effect it would have on the ozone layer, and also greenhouse gas removal in the troposphere, the lower part of the atmosphere. Then there's a major proposal, marine clouds, brightening marine clouds, creating new marine clouds. This is a new acronym that actually I've made up, MCC, marine cloud creation. And then there's a lot of serious discussion about restoring Arctic ice. I'm not going to talk about that today. So this is all about marine clouds. So marine cloud brightening. What is this? How does that work? How can you brighten marine clouds? Well, there's a nice little illustration here showing, I think there's a glass beads made from the same material in these 2 jars here, bigger ones and smaller ones. So that's all you have to do is make them more of them and smaller, and it's brighter. So brighter clouds, of course, they reflect more sunshine away than dark clouds. How do you do that? Well, cloud droplets need an existing aerosol to form over. They're called cloud condensation nuclei. So over land, they're abundant over land. It's things like dust and pollen and so forth. But over the ocean, especially over huge areas of ocean where there's nothing much growing in the ocean, they're very scarce. So you don't get so much clouds over much large parts of the ocean. But marine cloud brightening provides this powerful cooling opportunity. I was quite amazed when I saw this on one of Stephen Salter's slides. So I've written it in cool here. Earth could be cooled by marine cloud brightening to pre-industrial temperature. This is the subject of a paper by respected scientists. One of them works at the Met Office still, and he's a professor at Exeter University. So as you see, a few hundred vessels. I mean, this is a kind of artist impression of the kind of vessel needed. I think this is the main engineering challenge: producing a submicron aerosol large scale from seawater. But Stephen's arguing, put them in the right place at the right times. Okay, it's a lot of money, but what about the cost of not doing it? What about the cost of sea level rise and so forth? Marine clouds correlate with chlorophyll, it turns out. Once again, we were very amazed when we came across this from NASA. Anyone can you can look at it on NASA website, showing. So if we look at these areas where there is blue ocean, there's not much chlorophyll growing. By the way, it doesn't look like this. This is sort of a monthly amalgam of chlorophyll. Or anyway, it's computer generated. It doesn't. If you take a photograph, it doesn't look quite like that. So you can see that these blue areas here tend to correspond to where there's not much cloud. So once again, there's a potential for increasing the Earth's albedo. The photic zone is the upper area of the ocean, upper layer of the ocean, with phytoplankton growing in it. That's green algae. They emit this stuff called DMS, dimethyl sulfide. It's what gives the sea its smell, and also produces cloud condensation nuclei. So we know how it happens. And so the potential opportunity, if it could be allowed, and obviously it needs to be researched and tested, is these high nutrient, low chlorophyll ocean areas where it's rather blue. They're high nutrient apart from iron. So iron micronutrient is usually very low. It's usually extremely low, sometimes almost zero. And this is what's compelling. We think it could be applied as an aerosol. And why would we say it's nature-based? Well, this is what seems to have been the driver of the Earth's glacial periods. The last ice age ended only 20,000 years ago. There have been 4 during the last million years, very severe ice ages, fertilized by iron from the increased wind-blown dust. Here's a picture of dust blowing from an ice sheet, which would have increased the cloud cover over the ocean. And we know that atmospheric CO2 was around about 200 parts per million, sometimes less in some cases. So something was drawing CO2 out of the ocean, out of the atmosphere. And we think it's likely to have been the ocean doing that. Now this is a slight digression, this slide, but we're very interested. This has been a big part of Franz's research on the chemistry of iron aerosol in the atmosphere. There's a photocatalysis, which cut a long story short, depletes, very luckily, other greenhouse gases in the atmosphere, especially methane. Tropospheric ozone is quite a strong greenhouse gas and growing, and basically soot, black brown carbon. And also, very fortuitous, it turns out that ozone layer destroyers, things like so the methyl halides, as well as CFCs, which are very stable in the troposphere, they drift up into the stratosphere. This aerosol, iron dust aerosol, in the presence of sunshine, depletes them too. So in that way, it actually protects the ozone layer. So here's our proposal, Iron Salt Aerosol proposal. That's iron 3 chloride, or ferric chloride, to disperse that as an aerosol over the ocean, very small particle size, 100 nanometers, which would mean it would carry for up to thousands of miles in trade winds over the ocean. And we are suggesting a continuous, as much as continuous as we can possibly make it. We have to stop when it rains. Continuous application to allow ecosystems to grow and adapt. There's a somewhat positive feedback, self-reinforcing, mechanism that once you have an ecosystem, then it tends to, you have zooplankton and species swimming a long way up and down every day to feed on the phytoplankton. They bring up extra nutrients from further down. There's a lot more nutrients further down. How to get to full-scale production? Well, of course, as ever, funding, research and development. These headings were provided by Andy. Actually, I put these in as an engineer. I've added this one in, incremental scaling, in case anyone thinks we want to just suddenly do the whole thing without scaling it up. It needs to be, we need to have field tests done, and the results of each field test determine, how big the next field trial is, and during that time, you can start to design full-scale production equipment and so forth. That's it. So hope you enjoyed that. Hope that's useful. Before I stop, part of the purpose of doing these presentations and doing this, and we hope other presentations, is we want people to know about this, what's going on here, that these meetings that we're having, and that this technology and information is available, in case people would like to help us. We can't do it on our own. We'd love people to get involved. If you're at all interested, please send me an email to this email address, clive@endorphinsoftware.co.uk, and I'll reply and see what way that you might like to be involved. So that's it. Any questions?
If you would like to put any questions in the chat or raise your hand, and I will be able to unmute you.
The camera on now?
Oh, there is. I have put one question in the chat. So what experiments have been done to demonstrate your principles?
Well, so this, if I answer that from the Iron Salt Aerosol point of view, there were a whole series of tests that were done in the University of Bayreuth, I can never pronounce it, Bayreuth in Germany, where they tested the aerosol, and they were in the presence of an artificial sunlight, and they found very large amounts of chlorine atoms being produced, as was expected. So this photocatalytic reaction produces chlorine radicals, which are very strong oxidizing agents, and I believe it depleted. They didn't have methane in there, but they had other hydrocarbons which were depleted, so they were able to measure it that way. And just recently, that's been repeated in the University of Copenhagen, and there was a presentation recently at Cambridge Climate Repair by Professor Matthew Johnson, who, because there's been questions, could it work? We've got a $6 million question here, and he's been saying, yes, we haven't demonstrated. It's difficult to demonstrate it the way it would operate out in the the atmosphere, open environment, and they had rather small equipment, but he said there's everything to play for. It's looking possible, and that's Professor of Chemistry, the head of department at the University of Copenhagen. So I don't know if Stephen wants to say something about marine cloud brightening.
Yes, the first experiments were completely unintentional. People noticed that there were. Can you hear me all right?
Oh yeah.
Yeah. People noticed that there were sometimes very long streaks behind ships. The things called ship tracks. It didn't happen all the time, but sometimes they were really obvious, and that means that they had to have a contrast change that was quite a lot more than 15%. Otherwise, you wouldn't see them. And this is one of the reasons why people got interested in what caused the ship tracks, and it turned out to be the exhaust from the ships. But this was not an intentional experiment at all. It was just an accidental observation. There was one test done by Discovery Channel where they used cloud seeding flares from a ship and produced an enormous new cloud out of a completely clear blue sky, much to our surprise. we were claiming that we're only making existing clouds whiter, but we made quite a big one, lasted a long time. So the rest of the stuff has been done with computer models, and they confirm that it should work. I don't think they've all of them used the best size of spray, which I think is quite important. So up to now, mainly accidents or computers, with no funding, of course, to do anything but more than that.
Someone is typing in the chat. What happens to the iron chloride once in the environment?
Okay, good question. Well, it's an aerosol, so it carries in the wind, and eventually, in the atmosphere, it produces these chlorine atoms. It's quite complex actually, because the chlorine atom then goes off. Let's say if there's a methane molecule, it oxidizes the methane molecule, which produces a hydrogen atom. So you then get HCl vapor, and then there's HCl vapor exists naturally in the environment anyway, and then that rejoins at some point. You have HCl getting attracted back into the iron salt aerosol particle. The iron salt aerosol particle actually hydrolyzes a little bit, so it's a little bit wet in the atmosphere, and so the HCl joins it very readily, and kind of you could say recharges it with chlorine, so that it can then the next photon that hits some iron in the particle produces another chlorine atom. So that's why we call it photocatalytic, because it can produce many chlorine atoms. Chlorine atoms do exist. Radicals exist in the environment anyway, in the air, just not very many. So then, of course, at some point it settles in the ocean, and as a particle, it takes a long time to sink. Phytoplankton are extremely good at getting hold of iron in the ocean because it's in such short supply. They have all kinds of strategies of deciding whether to grab hold of a dust particle if they think it's got enough iron. Well, not they think, if it's got enough iron in it. And so once in the ocean, it basically fertilizes the ocean. The amount of carbon, this is called the Redfield ratio, where oceanographers have measured the ratio of iron to carbon in organic matter, and it's very high. It varies, but it's, I think, at least 1 in 20,000. Franz will be able to tell me if I've got that wrong.
I've heard 1 in 100,000.
Right, 1 in 100,000. Yeah, I think we've seen 1 in 200,000. That's kind of stretching it a bit. So I think we're sort of working on the figure of 1 in 20,000 to be a little bit, because thinking about CO2 absorption, but there's a whole other presentation to do about that, because it's not so straightforward as saying, all right, let's just cover the ocean with an iron aerosol. You have to think about, okay, so then what happens? Okay, that's what your question is. So then organic matter sinks. Well, first of all, ideally it gets eaten, and you grow the biomass. You have more fish in the sea. Fish poop out. They excrete their pellets. Some of them fall very rapidly to the bottom of the ocean, so that's quite a good way of sequestering carbon to the bottom of the ocean. But also, organic matter falls down and it oxidizes. So the carbon comes out again as bicarbonate, which is what it was when it was absorbed at the top of the ocean in the photic zone. That's, CO2 goes into water, it reacts with the water, becomes bicarbonate, and that's a feedstock for green algae. But if it's going to be remineralized back at lower levels, which is what happens naturally all the time anyway, you get increased acidity further down. So and then also it's using up oxygen in the water. So maybe that's enough. Maybe that's a longer answer than you expected. What happens to the iron chloride once in the environment? please say if you want to hear more about that, or if there's anything you'd like to me to expand on with that.
There are places in the sea near rivers where there's very, very much higher iron concentrations, and nothing terrible happens there. The fish are happy.
Yes, good point. Yes, thank you. Yeah.
Yeah, no, that was everything. Good.
Oh, good. Yeah.
Does anyone else have any questions? I've got another one if no one else is going to do. So at the start, you mentioned about the submicron aerosol from the seawater and that being a problem. What are the problems with that?
I think the main problem is filtering out all the materials that are in natural seawater. And there are some people who know quite a lot about inkjet printing and filtration who say this is a complete showstopper. However, the people who sell filtration materials to reverse osmosis are quite confident that they can do it. They say they're doing hundreds of thousands of cubic meters every day, and they promise that their filters, which are called ultra filters, will last. Well, they'll guarantee them for 5 years. They'll expect them to last for 10. And they grew out of technology that was developed when we had the polio virus. Before the Salk vaccine, people were infected with this dreadful disease that killed half of them and paralyzed the other half. And the polio virus was 30 nanometers, 29 nanometers, and they needed to filter water. And this is why the ultrafiltration modules will take out everything bigger than 20 nanometers. And of course, the filters get clogged, but what you do is you have a group of a lot of them, and one of them is always taking a fraction of the water from the others and putting it through the wrong direction. So it's called sequential backflushing. And we're really pretty confident now that we can do it. But we can test this quite easily by getting a group of 4 filters, connecting 3 of them in a backflush ring and feeding water to number 4, and just measuring the pressure across number 4. And if that stays steady, we know that the first 4 filters did a good job. So it's the biggest showstopper, and I think it's quite cheap to solve it one way or the other.
Thank you very much. That was a detailed question. Okay, someone is typing in the chat another question. Just bear with us. Does anyone else have any questions at this time? Oh, how is the energy balance for producing iron chloride?
So how much energy is used? We don't know exactly. We don't know exactly how much energy, but the effect it would have on reducing methane from the atmosphere, and certainly for assuming our tests are successful, CO2 from the atmosphere as well, would mean that whatever, if the fossil fuels, a good question. So if fossil fuels are used to make iron chloride, you want to make sure that that you're not making things worse. We think that it would be almost negligible. It would produce an almost negligible amount of extra greenhouse gas into the atmosphere, as would compared to what would be drawn back into the ocean, and methane oxidized to CO2. So, but we don't. It's fair enough. We don't know the actual. We'd have to go to one of the companies that makes iron chloride. Iron chloride is readily available. Actually, it's used in wastewater treatment and all kinds of industrial processes. So we'd have to find out exactly how much. It's not a bad question. We don't know the answer.
I can tell you how you can calculate it for marine cloud brightening. You need a number for the reflection from a cloud drop, and it's about 8 or 10%. So if you know your diameter of your cloud drop and how long it's going to last, you can say how much solar energy it will be reflecting. What you have to put into it is the surface tension energy to make the little seed on which the cloud drop grew, and that is the surface area of the drop, maybe 0.8 of a micron diameter. So you know the surface area of that, and then you multiply that by the surface tension of seawater, which is not quite the same as fresh water, very close to that, and the ratio of that comes out to many tens of millions. Depending on how long your cloud lasts, if it's 1 or 2 days. But it's absolutely enormous, and I don't know of any other mechanism that's got such a high energy ratio of the energy out to energy in. It's really absolutely astonishingly high. And we're making the energy from the wind. We're making it from driving the wind, driving spray vessels through the sea, and the motion through the water is generating the energy. So we're quite proud of our energy ratio, and it's a very useful number to calculate.
Thank you very much. We have another question. How would the weather be affected in places where marine cloud brightening is carried out?
It depends very much on where and when you do it, but there was some work done in Norway, in the Cicero labs in Norway, by a group led by somebody called Camilla Stern, and they had the brilliant idea of just spraying where there already were clouds, and the effects of this were a large increase up in the very high latitudes, in the say the ice in the Arctic, and there was an increase in precipitation in all the drought-stricken places, Sahara and Australia and California, Mexico. So it looks as though at least that way of doing it is really quite beneficial, but it will depend on where you do it and when you do it. And you might decide that you want to concentrate doing it where there's a nasty hot blob forming, or it's an El Nino that's growing. Another one is the balance of temperature across the Indian Ocean dipole, which sets the ratio of floods to bushfires in Australia and Africa. And one could have fleets of vessels that were cruising around the Indian Ocean, and if the Australians and the African countries can agree on a happy compromise, they can control the balance. I think the balance of temperatures across an ocean are just as interesting and important as the absolute temperatures. Wherever you do it, you're going to be helping sea level rise. And we think that some hundreds of vessels operating for 20 years could push back the sea level rise that we've already done. This is the heat in the deep ocean water, which is the biggest contribution. The melting ice is a bit, but the deep ocean heating is the biggest factor in sea level rise. So we need to learn how to drive the spray vessels in the right places at the right times, because the stuff is washed out by the next rain shower. It's got a fairly high frequency response, so you've got a lot of control over it, and you can learn how to do it. And I hope that it will be benign to a very great majority of the population of the world.
Are there any companies taking you up on your proposals at this time?
No.
There are two with Iron Salt Aerosol. There's one called Atmospheric Methane Reduction, Atmospheric Methane AMR. It's a Swiss company, and there's one called MOC, Methane Oxidation Corporation. So they are very young companies looking to grow and do their own R&D. We're all kind of associated. We try and be friends, even though we're kind of in competition with each other. But yes, there are people who see opportunities.
And we've got another question come through. Can aircraft crossing the main oceans be utilised for seeding?
I guess that would be marine cloud brightening, would it be?
They want to fly higher than the marine clouds, and it's very uncomfortable to fly low down over the ocean. I've done it, and it is the most sickening thing you can do. You may have noticed when you're taking off that you go through quite a lumpy bit, and then it suddenly gets calm as you go over about 1,500 feet. You could do it, but it's a very expensive way to move material around, and I think we don't need to, because if you release anything at the sea level, the turbulence in the air will mix it through the bottom of the boundary layer to get a fairly even distribution. The falling velocity in still air is so slow compared with the turbulence velocities that it's like putting cream in your coffee. You know, a quick stir and it's a fairly even mixture. So we don't need to use airplanes. They were used by Sean Toomey when he was measuring the cloud brightness, and he flew over them and measured the light coming down and the light bouncing up, and then he flew into the cloud and scooped some drops and measured them. But it's really quite difficult to fly low for a long time.
I just say that Iron Salt Aerosol, we did a presentation, excuse me, a couple of years ago at the IMechE, and one of our associates, a French chemist, Renault director, made the presentation, and I'm sure he had a slide that had a picture of an aircraft releasing Iron Salt Aerosol, but we don't really think that we want to do it that way anymore. We wouldn't want it. Similar reasons to the ones that Stephen's just given. Doesn't need to be that high, expensive. So we would do it from some kind of chimney that would give off the aerosol, and it would spread in just carrying the air and stay mixed in the air for the same reason that Stephen's just said.
You could do it from oil platforms, empty, unused oil platforms.
Funny you should say that, Peter. Stephen, that's exactly that. That's the picture on the AMR website, actually, a picture of an oil platform.
Yeah, I think you can reckon if you're getting rid of the methane, it doesn't matter quite where you do it. Marine cloud brightening, it does matter where and when you do it. But if you're getting rid of methane, it doesn't matter at all. Any bit of methane will do. So you'll spread around, and you don't need to be in a special place at a special time.
Well, we actually want to be where the sun is strongest for longest, because it's a for methane depletion, because it's a photocatalytic reaction, and so the subtropics, but preferably where it doesn't rain much, because you have to stop when it rains. So yeah.
Thank you very much. Are there any other questions out there? I have done all of mine, I have thought.
I'd like to ask a question. Why are people hostile to us?
What was that?
Why are people hostile to these ideas? There's much more money going into attacking it than into researching it.
You can answer that, Clive.
No, I mean asking people, I guess, to think of the answer to this. It's really big puzzle to me why people not funding any research.
It's certainly thought-provoking for certain. That's that's a question across my mind. I forgot to mention in the introduction that I first met Clive 2 years ago at the IMechE headquarters in Birdcage Walk for the presentation given about Iron Salt Aerosols, which was presented by Sir David King, and from that moment on, I mean, I still worked for an oil major at that time, and from that point onwards, I was on the hook, line and sinker. I was sold, and I just felt compelled to try and do anything I could to help out here. So, just to compound what Stephen said there is, why do people attack this? I think it's pure ignorance. people need to be educated, or at least given the facts that they can make their own minds up without listening to what's just radiated from TV. I would encourage anybody on this call or anybody that's attended tonight to please reach out to Clive or Stephen, and with any offers of help, or if you wanted to get involved, because it's the more I've looked into this, the more compelled I've been to try and help where I can. I don't know if I'm helping or hindering you gentlemen there, but I'm just trying to, get everybody, all hands to the pump at the moment, which I think certainly some of the professional engineers out there have certainly got a lot to offer.
I would very much like to have an engineer check all my design calculations and look at the drawings and point out where I've made mistakes. I've been trying to do that, and it's much, much harder to do it on your own. You have to leave something aside for 6 months and then come back to it to see what you've done wrong. I want somebody else who can do that more quickly. There's yards and yards of algebra design equations and quite a lot of drawings right down to component level and special bearings and stuff. But I need someone to look at it. Younger than me as well.
Sorry, what was that last thing you said, Stephen?
Somebody younger than me.
Someone that's younger than you, right?
Yeah.
I mean, and even if people, that's definitely helpful, Andy. What you were saying, in my view, if people feel that they don't know this subject, well, I mean, I didn't know anything about it until I started, volunteering with Franz. And Renault and that sort of crew on Iron Salt Aerosol, and it's very much a learning experience. We know that there's a lot to learn, so we have these fortnightly meetings where anyone's invited to just sort of sit and listen or ask questions, and it just sort of it takes people up. I'm just remembering. I've got a book by Professor Michael Mann. He's a climate scientist, and he talks about this sort of unintended consequences of geoengineering. So this stratospheric aerosol injection, people are rather worried. And he quotes the old song. There was an old lady who swallowed a fly, and then she swallowed a fly swallowed a spider to catch the fly, and a cat just she kept on swallowing bigger things until she swallowed a horse, and she's dead, of course. So he's saying that each solution becomes a bigger problem, that then you end up destroying the whole thing. But this is why we have this focus on nature-based, and I think people just conflate anything that's trying to help, with some other thing that is a bit less, a bit not as safe, such as stratospheric aerosol injection, in our view. So the trouble is, if we all diss each other's solutions, then that's not going to get us anywhere either. So I do like to, I do give time to the SAI people, and especially to Stephen. But I can't see how marine cloud brightening can do much harm at all.
There's a vast amount of salt already being thrown up into the air by breaking waves, and some of it's bigger than our stuff and falls down very quickly, and some of it's smaller. And it just happens that the natural aerosol is, you just thought it would be fairly even distribution of sizes, but that isn't true. There's 3 different sizes, and we want to spray in the gap between the present sizes. We want to be the middle size mode is called the accumulation mode, and we want to be at the very bottom size of that. And rearranging the size distribution of a material that's medicinally benign doesn't sound very, very dangerous. And what we're trying to do is to put the sea surface temperatures back to where we like to have them before, maybe 100 years ago. So that also ought to be a benign thing if we can do it. And adjusting where and when we do it may allow us to tweak monsoons and do other good things as well. But it's if you look at the amount of salt that's already there, it's enormously much more than we're trying to shift around. We're just changing the size. It's not much different from moving the furniture in the room.
I'm wondering if Franz, if you had any comment to make from any of these questions or anything at all, Franz.
I think the methane could be a really terrible shock if it comes off in a burp. It really would be the end. And there's so much methane there already loaded and waiting to come up. And a very small change in the sea surface temperature could trigger it. So that's why we need to have a methane removal method.
Yeah.
I would say, Clive, maybe you can better translate it. My English isn't the best. The dust in the ice edges, they put down as well CO2 and methane.
Yeah.
In the warm times, there was no dust, and in the coldest times, there were much dust. And then the CO2 and methane went down, and it's very easy to see. And even volcano outbreaks, volcano eruptions produce ash, and this ash behaves like Iron Salt Aerosol. And it contains much of acid chlorine, and produce in the sunlight lots of chlorine radicals. And this has been measured also by the Max Planck Institute in Mainz.
And I think they measured, did they measure lower concentration of methane in these places as well?
Yes, also.
Yeah, which is from the chlorine radicals oxidizing the methane. Yeah, because methane is otherwise a little bit, well, it takes a long time. It's hard to say it's stable, but I think it's one of the more it's the most stable of the aliphatic hydrocarbons. So ethane, and propane tend to oxidize more easily. Methane hangs around longer. I mean, it is half gone in, what is it, sort of 10 years or something. But methane's more than doubled its atmospheric concentration.
The IPCC say 28 times more dangerous than CO2, but that's averaged over 100 years. If you've got just a simple exponential decay, 28 times CO2 over 100 years is about 200 times worse than CO2 in the first year. But it may be that if you have enough methane, it'll be using up the materials in the atmosphere that are required for breaking it down. So we could suddenly find that its half-life is longer because there are not enough chlorine or hydroxyl radicals or whatever it's used to get rid of the methane. We need to know a bit more about the chain of decay mechanisms. But it could be really bad in the first year, and bad things could happen in a few months.
Yeah, that's what we're a little bit worried about. If there's global dimming, then you get less UV to make OH radicals, as you've just said, hydroxyl radicals. So if you've got less OH radicals, then you've got less, essentially, sort of natural cleaning that goes on in the atmosphere, including depleting methane.
Cosmic rays make it as well. That could vary out without our control.
Right.
Well, thank you very much. I don't think there's any more question coming through. So, yeah, thank you very much for the presentation and the Q&A afterwards. So, I'd like to give you a virtual applause.
Thank you very much. Thank you.
Yeah, thank you very much, and we'll let everyone head off to their evenings. So,
well, thank you for having us, Jenny. Much appreciated, and for recording the presentation.
Not a problem. So if you would like to get involved, contact Clive or Stephen. It will send you a link to this video, the recording on YouTube, and well, there it is right now. But they'll also contain it. So sorry, what was
our software address? Sorry, our email addresses.
Sorry, far away, Jenny.
No, I was going to say, well, there's Clive's email addresses, and if you would like Stephen's or Franz, then just contact myself. I'll send out that when I send this out. So, well, thank you very much for your time, and hope you all have a lovely evening.
Thank you very much.
You too.